In this video, I'm going to go through the review session questions that were presented in class on Thursday. First question, write the electron configuration for gallium. We're assuming this is a neutral atom. So let's go ahead and look at this on the periodic table. So gallium on the periodic table is number 31. So it's number 31 on the periodic table. So gallium, we're going to start by filling in, so again, if it's number 31, we assume it has 31 electrons. So let's start by filling in our configuration. So we have 1s2. Since that's full, we're going to move on to the next energy level, which is level 2. So we have 2s2, and then we have 2p6. So far, we filled in 10 electrons. So we've got the 2, and the 6. Those should add up to, or those do add up rather, to the number of electrons. We filled 2p, so let's go ahead and move down to the next level. So this is going to be 3s, and s holds 2. And then we have 3p6. So at this point, we're up to 18 electrons. So let's look at the periodic table. After we get to the third energy level and move down to the fourth energy level, that's when we bring in the D sublevel. So we have 4s2. So now we're up to 20. The D level is one behind. So this is actually going to be 3D. And then we're at, let's see, 20. We need another 10. So 3D10. Okay, so let me just count these up. So we're up to 20. Let's see, 20. Now we're up to 30 at this point, and then we have 3p. Oops, I messed up here. Not 3p. This is going to be, let me find the eraser on my pen here. This is going to be, apologize for that. There we go. This is going to be 4p1. So let me just do some math here to make sure that I'm right. So up to this point, I have 10, and then there's another 10 here, there's 10 here, and then boom, there's 31 electrons. And if I go back to the periodic table, we can see if we go to the fourth level that gallium, number 31 here, is the first element in the P block on level 4. So then I know that I've done this correctly. All right, number 2, it says write the noble gas configuration for cadmium. So let's go ahead and find cadmium on the periodic table. Cadmium is cadmium CD. Here it is. Cadmium's number 48 on the periodic table. So we're going to go back to the noble gas. So we're going to go backwards until we hit a noble gas. So after 37, we're to 36. So krypton is the first noble gas that we run into. Krypton. And then when we write our noble gas configuration, we need to write everything between krypton and cadmium. So from krypton, we have the 5s block. So let's go ahead and fill that in. So we have 5s2. 5s2, and then we need to get all the way to the end of the D block here. So this is going to be 4D, and then since we're all the way to the end, this is going to be 4D10. 4D10. And that's it. Fill in the orbital diagram for chlorine with a positive 3 charge. So if we go to the periodic table and look at chlorine, chlorine has 17 electrons normally. So 17 electrons normally, but since it's a positive 3, we know that it has 3 more protons, or rather 3 fewer electrons. So 17 minus 3 is going to be 14 electrons. So we need to fill in 14 electrons on our diagram. So 1, 2. 1s is full, so we can move to 2s. 1, 2. So we filled in 4 at this point. When we fill in 3p, we're going to go and make sure everybody has first before we go back and fill in for seconds. So let's count here. I have 2, 4, 6, 8, 10, 11, 12, and then 13, 14. And that's it. Now, on the 4p here, we want to make sure that we're not doing it like this. We're not going up, down. We want to make sure that everybody gets first before we go back for seconds. All right, predict the charge of indium when it ionizes. So let's find indium on the periodic table. That's In, and that is 49. So you can do this a couple different ways. You can go by the group numbers on the periodic table, or you can count backwards from the noble gas. So this is 8, 7, 6, 5, 4, 3 valence electrons. 3 valence electrons. Okay, so since it has 3 valence electrons, let me just write this off to the side. If you have between 1 and 4 electrons, you are going to lose. If you have between 4 and 7, you are going to gain, and I'm going to clarify here, gain to 8, because we want to have 8. If we have 8, you're cool, nothing happens. You have a full outer ring. Okay, so indium has 3 valence electrons. It's going to lose those. So my charge, since we have 3 valence electrons, is going to be, since I'm losing, going to be a positive 3 charge. We're losing electrons, and if we have more protons than electrons, we end up with a positive charge. What factors determine a metal's reactivity? There are 2 that we talked about in class. Number 1 is atomic radius. And if you think about atomic radius, kind of like magnets, so here's my nucleus, all right? If my electron is really close to the nucleus, there's a strong attraction here. If my electron is further away from the nucleus, there is less of an attraction here. So with 2 magnets, if you have those magnets really close together, there's a strong attraction. If those magnets are further apart, you feel less of an attraction or no attraction at all. And when these electrons are further away from the nucleus and there's less of an attraction, they're more likely to kind of react with other things. So atomic radius is 1, and then number 2 is the number of number of protons. So as we have more positive charge building up here, there's more protons in the middle, that electron has a much stronger attraction to the number of protons. So when there are more protons, there is less of an attraction. Oh, I'm sorry. That was backwards. When there are more protons, there is a stronger attraction. Stronger attraction. And when there's a stronger attraction, those electrons are less likely to react. What factors determine a nonmetal's reactivity? So nonmetals want to have 8 valence electrons. So on the periodic table, if we go and look here, nonmetals are kind of in this area over here in the green. And we know that the noble gases all have 8. So all of these nonmetals, they're close to the noble gases. So the closer they are to that, the more reactive they are. So if you look at the halogens over here, which is this last column, they are really close to 8. And they really want to get that last electron, so they're going to react. Okay, so fluorine is the most reactive in the halogens, and a good way to think of this is the nonmetals, the closer they are to fluorine, the more reactive they are. Okay, so let's move on. I think the analogy that I gave in class on this was like a collector. If you have almost an entire collection and you're just, one piece away from having a full collection, you're going to do pretty much anything you can to get a full collection. You'll spend all sorts of money, you'll do whatever it takes, you'll do all sorts of crazy things. Atoms or rather non-metals, kind of behave that same way. All right, what group on the periodic table is the least reactive? That is going to be the noble gases, because they already have a full outer ring. Full outer ring. Okay, so they've already got 8. They're cool. They don't want anything to do with anybody. They are good to go. They don't want to get into trouble. All right, so let's rank the reactivity of these metals. We've got Sr, Rb, Li, and Be beryllium. Okay, so let's go and first look where Sr is on the periodic table. So Sr is number 38. Rb was another one, rubidium. And then what else do we have? Lithium and beryllium. We have lithium and beryllium. Okay, so on the periodic table, metals are most reactive as they go to the left. So as the number of protons decreases, and then as we go down, we also notice that the atomic radius increases. So those two factors we talked about earlier. Okay, so if you look on the periodic table, rubidium is furthest to the left and furthest down. So this is going to be the most reactive. And then next to rubidium we have strontium, so Sr. And then if we go up to the two that are at the top, lithium and beryllium, lithium is further to the left than beryllium. So it would be lithium and then beryllium, just like that. Okay, number 9, we're looking at nonmetals. Now right off the bat, if you look here, radon is a noble gas, so it is going to have pretty much no reactivity because it's already content. So we also have iodine, carbon, and silicone. So iodine, carbon, did I say silicone? I meant sulfur. Iodine, carbon, and sulfur. So sulfur is almost fluorine. So sulfur is going to be the most reactive of those. And then what else do we have? Carbon and iodine. So carbon is 1, 2, 3 spaces away. Iodine is 1, 2, 3 spaces away. But iodine is closer. Iodine's in that halogen group, so iodine is going to be more reactive than carbon. Remember, the halogens, which are group 7A, are the most reactive. All right, let's look at number 11. Rank the activity of these. For some reason, I have this question in there twice. I will fix that for tomorrow. Let's go ahead and move on to number 11. Classify the following element. So shiny, good conductor, reacts with acid. All 3 of those are characteristics of metals. Number 12. It's dull, a moderate conductor, and reacts with acid. So dull makes you think non-metal. Reacts with acid makes you think metal. And then we have this moderate conductor. So most metals are strong conductors, but a moderate conductor is kind of in between. So this one, since it has characteristics of both non-metals and metals, I would say this is a metalloid. Okay, and again, for some reason, I'm repeating questions. All right, let's look at number 14. What is the charge of the carbon atom with this electron configuration? So it tells us that it's carbon. So carbon has, I think, 6 electrons. Let me go back and check. Yes, the neutral carbon atom has 6 electrons. So 6 electrons normally. This one has 2, 4, this one has 11. This is kind of an extreme example here. Actually, I'm not really a fan of this one. I kind of made these questions up by myself, but we're just going to go with it. So there are 11 electrons showing in the electron configuration. So in this case, there are, let's see, 5 more electrons than what you normally have with carbon. So, I mean, this This is a little ridiculous, but this would be a -5 charge. Usually you're not going to see anything like that. You're going to see maybe a 4 at the most, but in this case, because I'm terrible at writing questions, we have a -5 charge. Okay, what is the charge of the iodine atom with this noble gas configuration? Let's take a look. So iodine on the periodic table is 53. So it normally has 53 electrons. And let's go to krypton on the periodic table. Krypton has 36 electrons normally. So krypton has 36 electrons. And then I see an additional 2, 4, and 14. So there's another 14 electrons in the configuration. So if I add these together, I get 50 electrons. So I'm basically taking the 36 from krypton and then adding it to these right here. So I have a difference of 3 electrons. So there are fewer electrons shown down here in the electron configuration. So that means that there is a, let's see here. So there are fewer electrons than you normally have, so this is going to be a +3 charge. All right, got a couple more here. Hopefully no more repeats. Hopefully I worked that out. For 17, what's wrong with this diagram of phosphorus? Well, there are several things wrong with this diagram of phosphorus. If you look at the 2s orbital here, this isn't full. So we started to fill the 3p orbital before we finished the 2s orbital. So that's one. Always want to make sure they're full before moving on to the next one. In the 3p orbital, I see here that we have 2 electrons that don't have opposite spin. They should always be going one up, one down, indicating an opposite spin. In the 4p orbital, we should have filled all of them like this first before we went back and added a second one. So this should look like this. All right, what are the reactivity trends for metals and nonmetals? For metals, it is to the left and down the group. These are the most reactive. And for nonmetals, they are normally to the right and up, and then we're going to say with the exception of the noble gases. Because remember, those don't react. They've already got 8. Draw a diagram for an atom that shows an electron transitioning from the 4th energy level to the 2nd energy level and energy being released. Okay, so we've got our nucleus. Let me draw here. So this is n equals 4. The second one will be 3 and then 2. So we've got going from 4 to energy level 2, and then we've got our photon being released. That's pretty much it, just like that, because this would be n equals 3 and then n equals 2. Good enough. What color of light has the longest wavelength? For this first one, red has longest wavelength. And when we talk about wavelength, we're talking about the distance between the waves here. The most energy released is going to be violet. So violet has a very short wavelength, but there's more waves. So if you think about a jump rope, if you're shaking it, if you're really tired and you're shaking it, you're going to get something like this. They're going to have long wavelengths, not very many waves. But if you have lots of energy, you had a Starbucks nitro cold brew before you started to shake that jump rope, you're going to end up with something like this. You're going to shake it really fast, and there's going to be short wavelengths. So when we talk about most energy, think about Starbucks and shaking a jump rope, if that helps. All right, finally, rank the reactivity of the following elements. So let's go ahead and look at the first one. So it's krypton with 5s1. So krypton with 5s1 would be rubidium. Or kind of just write this down. Krypton 5s2 44. Krypton 5s2, and then 4, 2, 3, 4. That'd be molybdenum. Probably mispronouncing that. And then argon with 4s2. Excuse me. Argon with 4s2 would be calcium. So if I were ranking the reactivity, rubidium would be the strongest, followed by calcium, followed by molybdenum. So let's go ahead and look at this on the periodic table. We've got rubidium, calcium, and then we had molybdenum. So rubidium, obviously, farthest to the left. Calcium is the next furthest to the left. And then molybdenum, even though it's further down than calcium, it's really far to the right. So the atomic radius is a lot smaller in this case. Okay, and that's it.